Hi, my name is Rebecca Fath, and this is my Lab 9 Part 1 about the spring mass system. And the object of this lab was to use the momentum principle and the energy principle in order to model a spring mass system that was changing in both the x and y direction. And in the end, we went to compare the prediction model with the actual results. My observations were that the prediction model made from the momentum and energy principles was a good model for the actual results. So what we first did was we looked at this video in Tracker, and as you can see, it just dropped, and you can see the spring. It's the mass is moving not only in the x direction but in the y direction, which is something a little different we've done before, but nothing we can't handle. And so here we recorded the x and y values, and we put that in a CSV file so that we can later compare these actual results to our prediction model. One of the very important things we have to do at first is to find our initial values, and so that we can use them in our calculations for the momentum principle. And so we were given the ball mass and the ball initial position as found in Tracker. Here we use our initial position there. And then ball velocity, as you saw in the Tracker video, Dr. Greco had just dropped the mass, so no velocity was added to it. And then G is our constant, which has always been 9.8. And so then I used these values, and the first thing I wanted to find was our spring constant. And so I used the time period equation and reorganized it to isolate the spring constant. And then I got the oscillation time period of 1.52 from Tracker by looking at our graph here. And then I used that in order to find my spring constant of 6.869. I then used these values in order to find the relaxed length. We knew that, as you can see in Tracker, we did our calibration that with the mass on it, when it was relaxed, or it was at rest, it was only 0.7 meters. But what we also need to find the length of the string when there is no weight on it. So I used this equation, and then found S using our force and our spring constant we just found, plugged everything in, and got a spring constant, or relaxed length, of 0.1265. And I used these initial values and I plugged them into my Tracker code, and just as my initial values, so that I can use these constants throughout any of my momentum equations. Now, something different with our Tracker is that we've done momentum principle before multiple times, but something new is the energy principle. The energy principle is that the change in energy equals work plus scientific heat. In this case, we know that no heat is lost or gained in the system, so we can just say that equals 0. So in this system, delta E equals work. The three types of energy we need to worry about in this system is kinetic energy, which is 1/2 mv squared, the spring constant energy, which is 1/2 spring constant, the change in length from the position to the relaxed length squared, like that difference, and then the gravitational potential, which is mgh, and h is our length at the time. And so we use the change in these energies to get our total change in energy. And so this is something different we've used before, and it's very interesting to kind of see how they have an impact on our code. And we'll see it as, after I run it, you'll see the graph and you'll be able to see the different energies. And then you can see over here on my model that the blue ball is the actual and the orange is the predicted, and you see they're following fairly close along, which means that it is a good model, as I said in my observations before, and so we can say that it is a good model. That's one what does it mean questions. Comparing the oscillations of x and y. After comparing them, as you see in these graphs, the x oscillation was shorter than x time period of x oscillations was shorter than that of y. And I only think this was because that after the first displacement, x had a larger displacement in the beginning than y did, and so that it has, like a spring, it has that in effect. Like it's not going to continually pick up. It's going to have a very similar type of oscillation down the road as well, and so that time period doesn't really change. And so once x had a a larger displacement in a smaller time period, it just kept that way. And so our oscillations of x are larger than our oscillations of y. So our system here was defined as the mass, the spring, and the earth. And so if we were looking at that, and we had said earlier in our energy principle that delta E was going to equal work. Well, there is the work of the surroundings done on the system. And in this, there is no surroundings acting on this spring at all. So work here would equal 0. And a really cool thing we can do is if we run this again, you can see that this yellow line is the work, and you can see it's a fairly straight line staying to 0. And so that shows you that the work is 0, because like all the kinetic energy, the potential energy, the spring, and the gravitational all add up together, and you get this work of 0. So then we can say the work of the system is 0. If we were to put the spring outside of, or have the spring just be our system and the mass and earth be our surroundings, then that would change how we format our equation, and work would no longer equal 0. What would happen if we change the ordinance so that y equals 0 when the mass is at rest at static equilibrium? So if we change our y as you can see, this really has a huge impact on the magnitude of our string potential and our gravitational. It's just, it completely changes the system that we've had here. And as you can see, he's comparing it to the blue ball. It's completely different than what we had before. It has, since it started at such a different height, because it started all the way up at the top. If we run this again, you can see it again. Sorry. It started so high, so it had a huge gravitational potential, and that really had effect on the forces and how the system would run. So this is my lab, and thank you for watching.